Okay, the next lesson is going to be on L'Hopital's rule. L'Hopital's rule deals with finding limits in the indeterminate form. Now, we're going to look first off at a couple of problems that we've done in the past. This first problem is the limit as x approaches 3 of x squared minus 9 over x minus 3. Well, if you look at that problem and remember what we did in the past, we said, okay, if we plug in 3, we get 9 minus 9, which is 0, over 3 minus 3, which is 0, and that's 0 over 0. And I mentioned when we talked about limits, seems like a long time ago now, that there is still a possibility that a limit existed here. And what we did to see where that limit existed in the past is we said, okay, well, let's factor it out. This becomes x plus 3 over x minus 3 times x minus 3 here. And the x minus 3 is canceled out. You plugged in your 3. You got 3 plus 3, which was 6. And that worked. So we could simplify and then plug in and get our answer. And if you remember, this was what was called a removable discontinuity. You had a hole in the graph here. But it did not work for all of the problems. We got to the limit as x approaches 0 of sine of x over x. If you remember, we had to do something called the squeeze theorem on it. And we just memorized that this would be 1. But if you think about it again, what's happening here? Okay, we plug in 0, sine of 0 is 0, so it's 0 over 0. But we're going to look at another way we can do limits when they're in the indeterminate form. And these are different examples of the indeterminate form. We've got 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 1 to the infinity power, and 0 to the 0 power. Now you may think, well, 1 to any power is 1. Well, you're talking about this concept of infinity, or anything to the 0 power is 1. Well, what about 0 to anything? Doesn't that change things? So these are indeterminate forms, so we can use something called L'Hopital's rule. Now, any of these forms we would be able to take and write in terms of a fraction. So these are going to be our main two that we're going to look at. First one, we've got sine of x over x. Now, again, we know the answer here is going to be 1, but what L'Hopital's rule says is that we can take the derivative of the numerator, place it over the derivative of the denominator, and then plug in the value to see what happens. So let's do it for this one first. X squared minus 9 over x minus 3. Again, we already know the answer is going to be 6, but let's see what happens when we take the derivative. The derivative of x squared minus 9 is 2x, and the derivative of x minus 3 is 1, so we have 2x over 1, which is just 2 times 3 in this case, which would be 6. Now, one thing about L'Hopital's rule is, L'Hopital's rule, don't just think you can take any limit and take the derivative of the numerator, put it over the derivative of the denominator, and it'll give you the correct answer. It's got to be in the indeterminate form before this method works. So let's go to sine of x over x. Well, what is the derivative of sine of x? Well, it's cosine of x. What's the derivative of x? It's 1. So we have the cosine of 0 over 1, which is the cosine of 0, which is 1. So this is a lot easier, and it doesn't require us memorizing the squeeze theorem. All right, well, we have not even looked at this one yet. So let's see what's happening here. All right, we've got 2 times 0, which is 0. E to the 0 power is 1. 1 minus 1 is 0. And then in the denominator we get 0. So remember, it's 0 over 0, so there's still a possibility that we can have a limit exist. So we go into L'Hopital's rule. So we take the derivative of the numerator. All right, so e to the 2x, its derivative would be 2 times e to the 2x. And then the derivative of 1 is 0. And then the derivative of x is 1. Okay, So now we plug in 0 to this, so this becomes 2 times e to the 0 over 1, which is just 2 times 1, which is 2. So there is a limit that exists here, and that limit happens to be 2. Okay, now let's look at this last example here. This is the limit as x approaches infinity of the natural log of x over x. Okay, well, as x is approaching infinity, if you think about what's happening here, the natural log of x, its graph looks like this. So it does get infinitely large, but it gets infinitely large at a very slow rate. Now, we consider the denominator. The denominator is this value right here. So what's happening here is we have a gap that as we get closer and closer to infinity, this gap is getting infinitely large. So we're looking at analyzing what's happening there. So let's go into L'Hopital's rule. Again, plugging in infinity, you get infinity over infinity. All right, so the derivative of the natural log of x is 1 over x. And then the derivative of x is 1. All right, so now thinking about plugging in infinity. All right, 1 over infinity is very, very, very close to 0. So we're talking about 0 over 1, which is essentially 0. Now you think about that gap we looked at in the graph earlier. The gap consisted of the numerator was growing at such a smaller rate than the denominator was growing. And when that happens, we have a horizontal asymptote of 0. So that's the reason why we ended up with 0 as our solution there. So L'Hopital's rule is a very helpful way to find limits when they are in this indeterminate form. But again, make sure that you have it in an indeterminate form before you use L'Hopital's rule. One of the things you're going to see on your test is I'm going to say evaluate the limit. Some of the problems may not be in indeterminate form. Some of the problems you may just have to go in and plug in and get an answer there. But if they are in indeterminate, if they are for L'Hopital's rule, you will be listing which indeterminate form it's going to be in. It's going to be one of those two. But anyway, as far as this test is concerned. So I guess what I'm trying to say is there's going to be that check in there. You will need to be able to plug in for the limit before you can say, hey, I know that this one is where I need to use L'Hopital's rule. So I'm going to have that in there to try to catch you to make sure that you are off to the right track. So not looking, looking ahead, probably we'll touch on the linear approximation lesson real quick, and then I will be getting out an example of a practice test for you to practice on, of course, and then looking at probably the end of next week having your final unit test, and then we will look at going into the exam. Continue to take care. Your homework assignment is going to be listed below on the notes for this section. Bye.